So I'll share my screen now, and basically, I believe now you can see my screen.
Yes.
Yes,
It's clear.
great. So yes, honestly speaking, I myself don't like slides. I like to see the real action, and that's why today I'm going to do that. I'm not going to give you slides and so on and so forth. We'll just go directly to the software. Okay. Maybe you will notice something new here, which is I'm showing you the 2024 actually release, which is due in 2 weeks almost. We're planning to have a new release, although we had a release back in September. But this year we're making 2 major releases. The main reason is to the number of the release becomes fresh for the next year. So now the 2024 actually we're following. I mean, SLB in general is changing their logos. We're changing the even the icons of the software. You will see soon a new icon. It's not implemented yet, but the main change right now is that PipeSim name itself is not anymore capital letters as we used to have in all of our previous versions. PipeSim now is becoming just capital, the first letter. And as I said, there will be new icon probably in next year. So PipeSim in general, as you should know already, is a steady-state multi-phase flow simulator. And today we are going to focus on wells, meaning we're not going to show the network. We're not going to integrate the wells with the network or the pipelines. I'm not going to show the GIS capability or anything. I will just be focusing on wells. Before I go and build a new well model with you, or we go over how we build models or how we see the different options, I thought we go into a different way of introducing the software, which is showing you different examples that we already have today in PipeSim, and cover the different options there, run the model, have the different ideas about what PipeSim can do, and then at the end I'm going to basically take the user interface and build a model from scratch. So when you open PipeSim the first time, if you go to the workspace tab, you will find several options. One of them is help, and under help there is an option called button called case studies. Once you click on that, it will take you to the folder where all the existing case studies or previously generated models are stored. So there is a full folder for well models. So part of my webinar today is that I'm going simply to open this folder and go over the different, selected of course, different examples, and to have an idea on what PipeSim can offer. So starting with the basic oil well. So this is an oil well that has just one gaslet valve port. Okay. So I have opened now the first example, and let's have a look into this example, okay? And we will go into and see the different data. As you can see here, on the left-hand side, we have the well cross-section, okay? The well cross-section in PipeSim can be visualized by different ways. If I click on the Format tab, okay, I can make this well vertical, and all of that is visualization, right? So if I say 2D, it will take the basically similar to the deviation survey that I have in under the deviation survey tab, okay? And I can also look into the sectional view. Like, for example, if I say half, I can look into a different view where I can now have a look into the packer and the gas lift port. I can see full, and I can select quarter. This is just way of visualizing the well. Okay, so this is the default is the simplified half, in which we see the gas lift port as a a symbol, right? And you have a packer here like that. If you like for visualization purposes to improve that, you can select any of the format or visualization methods, right? So let me just go and make this vertical. And as you can see here, we have now a casing. This casing, the moment I click on any of the equipment here in PipeSim, it will take you right away to the tab where the information is entered, okay? In this example, we have one casing and one tubing, okay? Now, PipeSim, you will define the fluid path using packers. Like, for example, if I delete this packer, okay, or I make it inactive, you will notice that the flow in the annulus will be opened. Like when I deactivate this one, as you can see here, there is a new line, green line, that indicates there is the flow here in the well is tubing and annulus, right? Now I will make it active again, right? And as I said, when you click on any of the equipment, it will be highlighted, and then you will be able to change its data. Right now we have one completion. So when I click on the completion, it goes to the completion tab, as you can see here. And the IPR is described here. Like, for example, in this case, what we're using is, we're using a completion with a vertical geometry profile. Fluid entry is single point. And then since it is single point, I only define the middle MD. I don't define the top MD and the bottom MD. This top MD and bottom MD will be seen will be activated when we have distributed completions. The IPR type is Darcy, okay? And if you click on the IPR models, there is a number of IPR methods: well productivity index, Vogel, Fitkovich, Jones, back pressure, Forsheimer, and hydraulic fracture. However, this list is actually dynamic, meaning if I go now and change the geometry profile to become horizontal, then you will see that I have also additional IPR methods, Joshi and Babanode. So these are two additional IPR methods, but this is again for fluid entry single point. Now, if I go and make the fluid entry distributed, then there will be also additional two IPR methods, distributed PI and trilinear transient IPR, okay? So as I said, the IPR methods, the IPR methods available under this column here will really depend on the geometry profile as well as the fluid entry, okay? Now, let's go back to our original model. So what I'm going to do is that I'm going to make this single point, I will make this vertical, and then I will go back to Darcy, all right? Now, what do we have under Darcy, for example? So under Darcy, as you can see, the completion is selected. We have the reservoir pressure, temperature, the IPR bases, and then use Vogel below the bubble point. So I can, if I uncheck that, then it will be just a straight line. And now when I enable use Vogel below bubble point, then another option will become, which is Vogel water cut correction. This is an option that will model what is called composite IPR, in which if you have water cut, as the water cut increases, of course, then there will be less oil. And when you have less oil, the impact of gas on the IPR curve will be reduced, if you know what I mean. So just to describe, now this in this case here, okay, why do we have a curve after some time? This is because of the existence of the free gas, okay? There will be more pressure drop for higher rate. So this effect of or Vogel effect based on the availability of the free gas is going to be reduced as the water cut increases. And that's why if I go now to the fluid model and I say override method phase ratio, I can look into the water cut. So the water cut in this case is 0. And as you can see here, if I now enable this Vogel water cut correction, you don't see a difference because what? Because the water cut is 0. But the moment I go to the fluid model and I say the water cut is, for example, 90, when I go to the reservoir, you will see that it became more of a straight line, okay? And this is the effect of the water cut, and that's why we have this option, which is Vogel water cut correction. So let's go back to the original one. Let's go back to our original data. This is 0. And as a matter of fact, I can, you know, go to the override option and say none. When I say none, override method none, what does that mean? It means that the GOR and the water cut will be based on the original fluid description. Why do we have this option? In a network model, okay, you could have, let's say, one fluid file that is shared among maybe 30 or 40 or 50 wells or 100 wells, for example, okay? However, each well might have different GOR and water cut. So you can go to that well locally and override the phase ratio, okay? So you are still going to use the same fluid, which is in this case heavy oil. When I click on edit, I'm going to actually edit the original fluid. Again, this original fluid, if I have a network, can be shared by multiple wells. So when I change now the GOR and the water cut in the original fluid, it's going to be shared among all the wells in the network. But if I have a case where I have only one well, then it doesn't really matter. So you can change the phase ratio here in the original fluid, or you can change it in the override phase ratio. And by the way, there are also other places where we can change the override phase ratio, okay, or the phase ratio itself. So what else? Good. So now we had an idea about I clicked on the casing. So in the casing, you see we have the casing type. We have other casing types, such as liner and open hole, okay? So we can add, for example, an additional one. Once I open other examples, you will see what I mean here, okay? And the description of the thickness can be either by entering the wall thickness or the OD. So, like for example, if I have the outside diameter, I can put the OD here, and then I can enter the OD, or I can use the wall thickness. Why this is important? It's important if I activate the heat transfer calculation. Okay, that's why you will see that when I click on the casing or highlight the casing, you will see that the material of the casing will be described at the bottom. Like for example, here in this case, we see the thermal conductivity, the borehole diameter, and then the annulus material, cement density, and cement thermal conductivity. All this information is going to be used in the heat transfer calculation. We can also, there is also one functionality, which is to design a perforation, right? So there is a task called perforation design. If you open the perforation design, then these values will also be needed, because you will need the density in order for the perforation design to work properly. For the hydraulics, this is not needed, and that's why it is not mandatory. Okay. Click on the tube on the tubing, then you will see that also the tubing thermal conductivity is entered, as well as now the annulus material. Again, if you go to the heat transfer, Right now, I am specifying the heat transfer calculation. That's why this data under tubular is not going to be used, okay, in the calculation. But the moment I enable this and I say, okay, calculate the heat transfer coefficient for me, then you will need to enter the production injection time, and then there will be additional data such as the ground permeability and the ground conductivity, as well as the heat capacitance. Okay, so again, going back, I'm just trying to give you overall idea. And remember, for the people who just joined, I have already opened an example, a case study from the case studies that are stored with PipeSim when you install PipeSim. This is the very first case study, which is basic oil well. So in addition to, we have the tubing, we described the tubing and the casing. We described also the completion. We looked into the different IPR methods. And in this case, as I said, we have Darcy, okay? Now, under the completion tab, we have, as you can see here, the basic data for the reservoir, okay? And we have a tab for the sand. As you can see here now, it is not active. The reason it is not active is because this data is only used if I activate the Salama model. Like, for example, if I go to the simulation settings, and this is for erosional calculation, and I go to the erosion tab, you will see now I have two methods for the erosional calculation. API 14E, as well as Salama model. So Salama model requires certain data for calculating the erosion, and part of that is the sand production ratio, meaning part of sand per million, and the sand grain size. All of that is used in calculating the erosion using Salama model. Okay, and this is the erosion erosion velocity ratio risk index. So what Salama does is that it's going to calculate the erosional velocity using the sand data in the well only. Okay, good. So now going back to the API, so I'm just showing you different options. Okay, so now this is for the under the completion tab. I looked into the basic reservoir data. Of course, Darcy requires the reservoir thickness, borehole diameter, reservoir permeability. Okay, I can use relative permeability data if I want. Okay, and we have the drainage radius, and then we can also have a transient model. When we say transient, it's not really transient, but this will take the effect of time on the IPR. Okay, so what else? Good. So now we talk about that. Skin. So when I click on the skin tab, you can either specify the skin yourself or ask the software to calculate the skin for you. All these parameters here. Now, as you can see, the mechanical skin is 5.1. This is automatically calculated using the data that are available under the damage zone, the perforation, partial penetration, and deviation data, okay, as well as the compacting and crush zone and gravel pack. So if any of this data, like for example, if you don't have gravel pack, you can simply delete that, and then that's fine. It won't be taken into in the calculation. Okay, so now you can simply, as you can see here, but you need to activate something to recalculate the skin. As you can see here now, after I removed the gravel pack data, the calculated skin is changed. Okay, you can also specify the skin if you want. So if I don't have all this data, I can simply click on specify for both mechanical and rate dependent skin, and I can enter these values. If you have them from your pressure transient analysis, you can go ahead and enter this skin data. Okay. Finally, the fluid model. We have seen, I think, the fluid model before, where you can edit the original fluid here, Like for example, under the fluid, you can enter the API. As you can see here in this case, this API, the fluid is very heavy. This is the viscosity data. Okay, as you can see here now, we are using defined table for the dead oil under different temperatures. Okay. Also, PipeSim has the ability to determine the emulsion viscosity by using different methods, such as Wolfen method. We have different Wolfen emulsion calculations and other methods. Okay, and to learn more about the emulsions, you can simply go to the help. And as everything else, if you want to learn anything, just click on the help. There will be a lot of good descriptions here. Okay, but specifically for the emulsions, as you can see here, it says oil water mixtures, and then this is how you enter the different, or how to select the different emulsion calculations. One important thing is to understand that there is an inversion point in which, depending on the method you use. So, like for example, if I say set to the continuous phase, then what happens is that the inversion point is 60, and for example, which means that below 60, the viscosity will be for oil. Above 60, it's going to be water. But if I use the method itself, right? Like for example, if I say, okay, let me use Wolfen tight emulsion, then there will be calculation of the viscosity change with the water cut. Just to describe this a little bit more, if I go to the search and type emulsion, then I'm going to have one nice plot here. So this is the mixture viscosity. Okay, these lines, if I'm going to use the continuous line, and this is the Wolfen emulsion correction, and this is the inversion point. What does that mean? It means that as the water cut increases, the viscosity of the mixture will increase, and then until it reaches to its maximum, and then it starts going down to go to finally to the water viscosity. This increase in viscosity is due to the emulsion formation. Okay, so I don't want to spend more time on the fluid, but we have right now we have this is for the calibration, to calibrate the fluid. Right now it's a single point calibration. Very soon in next year we are going to have a multi-point calibration in which you can enter PVT table for the measured data, measured viscosity, measured the formation volume factor, measured the gas oil ratio, and so on and so forth, so that the fluid will be calibrated. Right now it is single point, meaning you need to enter one measured value at the bubble point, above the bubble point, or below the bubble point. And you have the thermal calculations. These are, I don't think you need to play with this a little more, but if you want to be to see the impact of the capacitance, then you can play with this. Okay, so again, this fluid description is for black oil. We have also the ability to model composition of fluid natively, but I'm not going to cover that for now. So what else I need to talk about this in this model? So we have, for example, one gas lift port. So once I click on the gas lift port, I see that I have activated the artificial lift tab. Okay, and as you can see here, we have gas lift. In the gas lift, we have two options. We have either fixed injection port or injection valve system. The fixed injection port is basically going to allow adding the gas into the oil at this depth without further calculations. I can either set the GLR, or gas lift ratio, to a quantity, or I can simply define the injection gas rate. I can say, for example, at this port, I am injecting 2 million standard cubic feet per day, and that's it. So what will happen is that this is just a simplified gas lift calculation in which the software will not calculate the effect of injection. it will just assign the gas lift rate at this depth, okay, to the fluid. If you want to have more comprehensive gas lift calculation, you can go to the injection valve system, in which you can have injection valves, actual injection valves from manufacturers. We have multi-pointing and throttling calculation. I will show that in another example. But for the time being, we're just going to use injection valve system, fixed injection port, and that's it. Surface equipment, you can have surface equipment added to the well. You can have, for example, any kind of surface equipment that can be seen in the network if you switch to the network canvas. But literally, I can add a sink, I can add a choke, compressor, surface pump, injection point, and so on and so forth. With that, I'm going to now to again go into the tabs. So in the beginning, when I described this example, I did not follow the logical flow of entering the data. I was just clicking on the equipment and then looking into the description. But I can simply go into the tabs right away and follow the logical input data. Like, for example, the first tab is the general, where you can define the well name. You can define the well type, whether it's production, injection, or advanced. For the advanced option, you can refer to my previous OPA presentation. I talked specifically about this option. And then you have the check valve settings. This check valve settings is very important when I integrate with the network. Deviation survey tab. For the deviation survey tab, there are different options. The main and most important one, of course, is the 2D, and of course you can enter 3D. For the 3D, you put the azimuth and the dogleg severity, but this will be enabled later on once we enable the 3D visualization. But for the time being, 2D is more than enough. So if you select the survey type to be 2D, you can enter the MD and the TVD, right? And then the angle will be automatically calculated. If you have the measured depth and the angle, you can make the dependent parameter to be the true vertical depth, and then you can change the angle itself. So let me do one thing. Let me show you how this is gonna work. So if I start by 5, and then I go to 15, and then 20, 25, and then 35, and then 50, and then maybe 75, and then 89, 90, 90. Now what do I have? I have now horizontal description, okay? And I can go, if I go to the format 2D, then it's going to take the deviation survey as I have entered it, okay? So this is the deviation survey, and of course you can put the original, there are different depth reference depending on the whether it's offshore, onshore, and then you can define the wellhead depth. Like, for example, if you have an offshore well, you can put the wellhead depth based on the seabed, okay? And then all this is going to be taken into consideration if you use the heat transfer calculation. Heat transfer tab, I think we have covered that. Tubular, we have covered that. Downhole equipment, this will describe all the downhole equipment that I have in the well, not artificial lift. So for example, now I have a packer, which is placed here. If I insert other equipment, if I go to the insert, and then, for example, I need to insert, let's say, a subsurface safety valve, I can drag and drop it, then it will appear here, okay? I can define the beam size of the subsurface safety valve. For example, it could be 3 inches, okay? And I can also define if I have, let's say, sliding sleeve. If I put a sliding sleeve, it will basically open the channel. Like, for example, here, what I can do is that I can, at certain depth, I can define a sliding sleeve, and then the moment I add the sliding sleeve, then I can define that at this depth, the flow type become annulus and tubing. I can make it only annulus by putting a plug. And now I have controlled the fluid direction inside the wellbore. Like for example here, from this point upwards, the main flow will be in the annulus. Okay. This is one equipment. There are also other equipment such as a spot report, for example, engine keyword, and these are the artificial lift equipment, right? So for this example, I'm not gonna do further description. Let's just run it and have a look so that we can have an idea about other examples. Okay. So again, this is a black oil fluid. All right. This is a black oil fluid. The completion is placed at 9817 feet. It's a Darcy IPR. This is the reservoir pressure, temperature. This is the permeability and the data needed by Darcy. Okay. This is the skin. So I can activate the calculate skin, or I can specify. Okay. Let's say I put, for example, 4 and 3. Okay. This is the fluid model. And then I don't have any surface equipment. With that, let's now go and run our model. Okay. For the simulation, in modeling wells, there are a number of, we call it simulation tasks, right? Of course, the most famous one is the nodal analysis. The nodal analysis is, of course, I'm sure most of you, if not all of you, know what nodal analysis is. I have also other presentations or webinars that I have done in the past talking specifically about nodal analysis. But in simple terms, nodal analysis will create two curves. One curve representing the pressure drop as part of the completion, and another plot represent the pressure drop as part of the wellbore. If we put the node at the bottom of the well, and then it will find the intersection. The intersection of the two curves will represent the operating condition. So now I did not enter any sensitivity. I will just click on the run button. So now this is our first simulation, which is a nodal analysis. Okay. Now, as you can see here, the fluid is I would say weak because I probably increased the skin. So let me just remove the skin. I will go to the completion skin tab, and let me just make those skin 0 and 0. Okay. And for the reservoir fluid model, let's use the well as is. So now if I go to the nodal analysis again, remember now the only thing I have done is that I have removed the skin. I hit the run button, and now this is our well now. So this is our IPR, and this is our VLP. Okay. Now, what else can we see in this simulation? So number one, we can see the intersection. So the operating point is the flow rate. So it tells you what is the stock tank liquid flow rate at the nodal analysis, and it tells you also the flow and bottom pressure. Okay. If I need to see more data, I can simply go to the profile results. The profile results will basically describe all the hydraulics at this flow rate and at this bottom pressure. Like, for example, click on profile results, you will see now a plot, but then this plot represents the pressure. This is the drawdown at the reservoir. We have significant drawdown, and this is the outflow. Okay, but I can go to show grid under profile results, and now I have all the results available for me. Okay, let me just expand this a little bit. Now, if I need more data, or I'd like to hide some of the data that's not relevant to me, I can simply go to select columns, And then I can activate or deactivate the columns that I'd like to see in this grid. For example, let us see that I don't want to see the case because I know the case, it's one case. So uncheck this case, then it's gone. Then I'd like to have additional data such as gas velocity. Okay. I'd like to see also the measured depth, for example. I'd like to see the pressure gradient, whether it is, you know, I mean, how are we changing? What's the, I mean, the pressure loss per foot, or probably pressure gradient is not important. Maybe we need to look into the delta pressure due to gravity. Like, for example, I can look into, if I say pressure, we have the frictional pressure drop and the elevation pressure drop. Okay. Now, as you can see here, I have now the data. I have the total distance, the elevation, pressure, temperature, fluid mean velocity, liquid holdup, erosional velocity ratio, and so on and so forth. Okay. Now, you will notice here on the column that has the numbers, there are certain rows with a plus sign. So when I click on this plus sign, it will expand the details. So I will see more description. Like, for example, in this case, it's a completion. And then under this completion, you will be able to see the static pressure, the flowing bottom hole pressure, the drawdown pressure, temperature, okay, flowing temperature, the liquid flow rate, gas rate, and mass rate. And also you can go to the gas lift port and look into, you know, the flow rate. Now we have the you know, injection point temperature, and then we have the delta P and the joule to Thomson effective delta P are not calculated. Why? Because there is another, this is the simplest form of gas lift. So if I want to have more calculations, there are of course other options that I can activate under the gas lift. I can say Al-Hanati stability check, and then once I enter that, I will need to enter the injection pressure and injection temperature, and it will be taken into consideration in the calculation. So this is the nodal analysis. I know we're running out of time, so let's have another example to see what options do we have. Okay, so I will go again to the help, case studies, and let's have a look into the second example, which is basic gas well. So this is a gas well. It has a deviation survey. Now as you can see here, I'll be a little bit faster because now I'm expecting that now we're more familiar with the tabs and everything. Okay, so this is the deviation survey. Okay, we have the heat transfer is also specified. So I am specifying U value of 2, but you will notice something that now the MD is 160. And the reason for this is because the well head is at 160. Okay. Now, when it comes to this is the tubular, so we also have one casing and one tubing, right? Downhole equipment, we have only one packer. We have a nodal analysis point, and we don't have artificial lift. What is mainly different in this well are two things. Number one, the completion description and the fluid. So we are using the geometry vertical, fluid entry single point, but then the method IPR is back pressure. So the back pressure or the C and N value is mainly used when we have a gas well, right? And as you can see here, this is what we specify, the C and N, okay? And for that, you will also notice that I am using a different fluid icon, which is, if I click on it, it is compositional. So for the compositional, if I go to the component and model settings, I can define what is the PVT package. Under each PVT package, we have a list of equation of state. and then I can define the viscosity method. And now here are the components. So all these can be selected, but now I can define, if I just highlight the selected components, then I'm going to list what are the components that I'm using in my composition. Okay, so now if I scroll down, so we have now 10 components, including water. Okay, and now if I need to enter the composition, I go to the fluid and double click on the fluid. Or if I don't have a fluid, I can first define the components, and then I can go to the fluid and click the plus sign, click the plus sign, and then I can define my composition. When I double click on the fluid, it will open the compositional interactive screen. In this interactive screen, we have this one. In this interactive screen, we have the phase diagram. Okay, and as you can see here, the phase diagram shows you, it can show you an operating point. Like, for example, you would like to say, okay, what if the pressure was maybe 1,800 under the pressure of 200 at the temperature of 200? Where are we? Then you will know that you are at this point. This is now a very useful tool that is very unique in PipeSim, where you can use the interactive flash calculation using the compositional fluid, compositional fluid engine, to define what is the phase ratio. Okay, like for each of the components, you can define whether is it gas or liquid. Okay, and as you can see here, at this point, you know, most of it is gas, and you know, the liquid is very, very small. And as you can see here, the GOR is infinity, meaning that this is really gas. It has some condensate, but very, very small. And if I now go and say, okay, now what if the temperature was, what if the pressure was 1500, and then the temperature was, I just need to enter it here inside the phase diagram, and the temperature was 120, then you will see that now we have a GOR. Okay, we have now for each of the components, we know what are what's the phase ratio. Okay, for each of the components, and yeah, so on and so forth. So in this case also, we can see the water line, and then we can see also the ice line, and we can see the hydrate line. Okay, which means that if you cross this hydrate line, then there is a risk of hydrate formation. Now, this is the compositional fluid interface. Okay, and this is the IPR. So these are the two main things that are mainly different from the previous model. So now let's go to the nodal analysis and also run the nodal analysis again. And remember, this is not, you know, doesn't have any artificial lift, but this is also will show you the concept of sensitivity analysis into the nodal analysis. Like, for example, here I am changing different C values, and for the inflow, and for the outflow, I am changing the inside diameter. Okay, so I have different options for the inflow, for the outflow. When I run, I'm going to expect to see 12 combinations. Like, for example, when I click on run, you will see that I will have 4 inflows and 3 outflows. Okay, and it's taking, see now, so we have now a combination of inflow curves as well as outflow curves. Each outflow curve represents one diameter. Like, for example, if I want to read a specific case, I can simply bring those together like this, and then I can see the diameter and the N value. And it tells you at each combination how much is the flow rate. Okay, so this is showing you different IPR methods at different C value and different different IPR curves at different C value and different outflow curves at different diameter. Okay, suppose that you'd like to see the profile results, so you click on the profile results and then all of the cases will be shown here. Okay, and you can specify, you can add any additional profile. So this is the elevation, this is the pressure. You can of course change the index, the axis, and view the different results. We can see that in a different example. Okay, so this is the second case. Now, one of the important parameter that, especially for gas wells, is that I'd like to see if I have any problem of liquid loading. Okay, so I have removed now the sensitivities. I will run only one case, and I'll click on the run button. Of course, you expect that for compositional fluid modeling, it's a little bit longer, takes longer time because it's a more, of course, complex calculation. Now, if I go to the profile results, okay, and I go to show grid, okay, one of the things that I'd like to see is if I click on select columns, okay, and now there is an option here that says liquid loading gas rate, liquid loading velocity, okay, and liquid loading velocity ratio. Okay, let us now have a look, and you will notice something, that the liquid loading is only calculated at certain depths. The reason is because for the liquid loading to happen, you will need to have certain flow regime. Okay, and as you can see here, at this depth, which is at 3,160 and upwards, so of course this is flipped, huh? We're starting from the bottom to the top. Okay, then this is the liquid loading velocity, this is the liquid loading gas velocity, and this is the liquid loading velocity ratio. So in this case, it means that we do not have liquid loading issue because we are still below 1. The moment you have 1 or more, that means you have a risk of having liquid loading at this certain depth. Okay, I hope this is clear. Good. So let's have another example then. I will go to the help case studies again, and then well models, wellhead nodal. I will just this is another concept in which you can select the nodal point at a different position or different location. Like, for example, this is the same case that we ran before. However, you go now to the surface, and I have added now surface equipment. I have added a flow line, okay, under the surface equipment, which is the diameter is 4 and the horizontal length is 10,000. And then we have a riser. So the riser is actually going up, meaning, it's just a vertical pipe. And you will notice that our nodal point is actually placed at the wellhead, okay? If I click on the riser, so this is the riser, sorry, this is the top side, the sink, this is the riser. And as you can see here, we have the seabed depth, okay? We have the surface temperature, seabed temperature, and then we have also the U value for the water section. So as you can see, all of this is to calculate the heat transfer calculation. Okay. Now, one important thing is that In this case, I have not entered any choke, which means that the fluid flow, there is no restriction into the flow line and then the riser. Okay. Now, if I'm going to run the nodal analysis, okay, it is important that I need to define it. We just also remove the sensitivities. I'd like to mention that I need to define where is the branch ending. So if I want to include the pressure drop of the flow line and the riser, I have to say that my branch is ending at the top side, meaning it's at the last portion. If I do not do that, if I say the wellhead, then the pressure drop of the flow line and the riser will not be taken into consideration in my inflow and outflow. So I say my branch ends at top side, and then I click on run. You will notice that the inflow and the outflow will be calculated at the wellhead, right? And the pressure here is what? The pressure here is now at the nodal point, okay? It's not at the bottom hole, okay? And if I for example let's say change, let me just show you that if I change now the flow line diameter, okay, as a part of the sensitivity, you will see that the flow line will affect the outflow, okay, because the flow line is not as part of the inflow, because now we're putting the node at the top, okay. So let me show you that. So if I go to the inflow sensitivity, inflow and outflow, I will see that the flow line is part of the outflow, and then I can put the inside diameter, let's say 2 and 4 or 5 inches. Now when I run, you see now this is at 2 diameter, this is at 4. Now, what about the tubing? Is the tubing inflow or outflow? In this case, the tubing is an inflow parameter because my nodal point is at the top. So everything below the nodal or before the nodal point will be considered as part of the inflow. And that's why if I go to my nodal analysis, if I go to the inflow sensitivity, I will see the tubing here as part of the inflow. And then I can enter the inside diameter of the tubing to be, for example, 3 and 5. And when I run, I will see that I have 2 inflow, 2 outflow. And this is because I have changed the diameters of the tubing, which is part of the IPR. And I have changed also the flow line, which affects the outflow because my nodal point is at the wellhead. I hope this is clear. Okay. So this is when if I want to place my node at any location. And by the way, you are free really to select your nodal point anywhere. Like for example, if I delete this nodal point, I can simply go to insert, and then I go to nodal point. I can put it anywhere. Like for example, I can put it connected here. Sorry. At this point, or you can delete that, and then when you go to the downhole equipment, you can add a nodal point. Yeah, I need to run nodal first. So I go to nodal here. I have deleted now my nodal analysis. I go to the nodal analysis and it tells me, okay, where do you put it? If I say put it on the bottom hole, it will add it at the bottom of the well, but I can also change its depth. Like for example, I can put my nodal point to be inside the tubing. And now all the inflow will become before this node, all the outflow will become out after this node. What about the completion? So we're using the well PI, but now since so we're using the well productivity index. So that's why the data is simple. I can of course activate the Vogel correction. The fluid is black oil. So this is the second example. Third example, let's go to the well models, and then we can go to an unconventional oil well, or let's go to water injection well, for example. So for the water injection, so we have now, as you can see here, under the general tab, I have an injection. That well type is injection. Surface equipment, I have a source. I have a surface pump that is adding 100 horsepower. We have a downcomer. This is a subsea also well. We have a flow line, and then we have the water injection well. Okay. As you can see here, when you go to the well stream inlet, well stream outlet, I'm adding this fluid which is water in this case. If I go to the completion, this is a well PI, okay, and now I can simply run my nodal analysis, or run my PT profile, for example, and this is the inlet pressure. When I click run, now we have an injection. So this is the injection. This is the elevation. This is the pressure. So as you can see here, we have the pressure is increasing, right? And then why the pressure is increasing? Because we have the pump here, and now as we go down, the hydrostatic is also increasing. That's why the pressure is increasing as we go down. And then this is the pressure in the completion, right? That's why you have a pressure drop. And now the flowing pressure is higher than the reservoir pressure. Okay. One important thing I'd like also to share with you is the system analysis. So let me just go to a case study. I go to the well models, and then one good example I'd like to also to share with you is the geothermal well, but let me just do that in a moment. Okay, man, we're running out of time. Oh, sorry. So let us now, well, there are a lot more examples I'd like to cover, but let us start from building a well model, and then we are going to add some artificial lift to it. Okay, so I'm going to a new well. So new, and then a new well. This will be quick. You will see that. So now I'm starting a well from scratch. Okay, so I can simply drag and drop a casing, drag and drop a tubing. All right, this tubing now by default is 1.56. I can of course change that. I'll make it 3, and then the SI diameter of the casing is 6. And now I'll put the tubing that goes all the way up to, let's say, 8,000. Then what else? Do I need to insert a choke? No. A packer? Yes. So I'll put a packer. And then I don't need to enter a sliding sleeve. I can enter a subsurface safety valve here, for example. And then I will enter a completion. For the subsurface safety valve, it needs the diameter. So let's say the diameter is 2.9. And then, so I have added the completion. So let's enter the completion details. The default is well PI. So I'm going to enter the reservoir pressure of, let's say, 2,500. Reservoir temperature of 200. Productivity index of 5. And now we need to enter a fluid. Click plus. There will be a template for fluids. Let's use a heavy oil just to make it hard to flow. The GOR, I'm going to put a GOR of 200. Let's say 0.8 gas passive gravity. And now that's it. So my model now is ready. So I can now simply go to the nodal analysis and run my model. The node is at the bottom. So click on OK. And now wellhead pressure, I will put 300. Let us see if this well can flow under these conditions. So the well is not flowing. This is interesting. So now since the well is not flowing, I need to add artificial lift. Okay, so one of the methods is that I can design an ESP easily. Okay, so I'll add an ESP, and then I will remove the ESP and I will add a gas lift. Okay, so now the well is not flowing because the inflow, the IPR, the bottom hole energy, the bottom hole pressure based on the IPR is actually below 2,500. The outflow in this case is very high, which means that the fluid, since the fluid is heavy, with my depth, okay, it's creating a lot of pressure to the bottom hole. So that's why I need to reduce that bottom hole pressure on the outflow by installing an ESP. Okay, now how do I do that? Well, simply I can go to the ESP design, and now it will ask me what is the outlet pressure, how much is the operating pressure you need to produce. So I'll say, for example, for 300, this is my operating pressure. Now it brings you the inflow and the outflow, and this way in this screen here, you will be you need to become a little bit let's say you need to have some thinking here. Where do you want to bring the inflow and the outflow to intersect? Okay, so normally we need to pick up a point of the intersection where the VLP is going up. I don't want the intersection between the inflow and the outflow to happen on the left-hand side of the VLP curve. Okay, which means that if I tell the software I want the design production rate to be 1,000, what will happen? That means the software is telling you that I'm going to bring the VLP down to intersect at this point. But then what will happen? The intersection is happening on the left-hand side of the VLP curve, which is an unstable region. That's why you need to avoid that. So then which rate? So I'd like to produce at least at 3,000, because this is the pickup point, or maybe more. So I will tell him I need this well to produce 3,500. And now you tell me, you PipeSim, tell me what are the available pumps that will be able to do that for me. So now I click on enter. It now moved the green line, which means that this is where the intersection is going to happen. Now I go now to the pump selection. This button here, the moment I click on it, then at the back of the engine, there will be a calculation to select all the pumps available for you that can produce this rate, and he will order them based on their efficiency. So when I click on these three buttons, it's doing the calculation now. And now it listed for me all the available pumps that can do this artificial lift, and it will make the well produce 3,500. They are ordered by their efficiency, as you can see here. So let us select the first one. Now, when I select the first one, there will be another calculation that will happen, which is calculating how many stages are needed. So when I click on OK, I need to run another calculation. So when I click on run now it's going to use this pump, but then it will tell you now you will need 140 stages. And that is a lot, of course, but if you want this well, which is not flowing, to produce as high as 3,500 barrels per day, you will need to install 140 stages using this pump model. So now the calculation is done. We have now multiple plots or multiple curves that to analyze your data. Number one, we have this green line, which is the bubble point pressure. Okay. Now you are away from the bubble point pressure, which is good because you don't want the intersection or the bottom hole pressure to produce below the bubble point. These three different curves, or actually 5 different curves, are at different frequencies. And you will notice that the these curves, so this is the original IPR. This is the original VLP, okay? What does this mean? We know that depending on the nodal analysis point, the calculation of the inflow and the outflow will be identified. So in this case, the curves are changing the IPR curve. What does that mean? It means that in the calculation for this curve, the nodal analysis is placed at this depth, which is the depth of the pump. I think it's 8,000. Where is it? It should be somewhere. Yeah, I mean, it is 8, I think, where is it? Here, in ESP Design, yes. So it is at 8,000 here. And at the same time, the IPR includes the pump effect, which means that the nodal analysis point is placed above the pump. That's why we see these different curves, okay? Now, what else can I see from these curves? It tells you that at the frequency of 40, the well will not be able to flow, okay? So the minimum frequency that you can go with is 50 and above, okay? This is 50, this is 60, and this is 70, okay? What else? And that's why you see here, it says pump suction pressure, okay? This is the pump suction pressure or the IPR. Now, actual pump curve, this is the actual pump curve. This is the head added versus flow rate. This is the power, and this is the efficiency. This is the well nodal analysis. And now, in this curve, the VLP now is actually includes the pump, which means now this is based on the actual nodal analysis location. In this case, the nodal analysis location is at the bottom of the well. It's at the completion. And that's why the IPR, this is the original IPR, if you remember, it's starting at 2,000 almost. And now this is the VLP, including the pump. Now, as you can see here, designing a pump and installing a pump in PipeSim is really straightforward and simple, right? Although it is comprehensive, it does everything for you, okay? If I'm happy with this pump design, now I can simply go and click on Install ESP. Once I install the ESP, the pump will be added, and now I can simply look into my model. So now the pump here is added at this curve, at this location, at the bottom of the well. And now this is the pump details, okay? This is the ESP frequency, the base ESP frequency. This is the operating frequency. This is the number of stages, right? And now we can also have calculation options. Like, for example, if I would like to also calculate the ESP power at the surface, then I need to also go into the surface power correction. When I click on that, I can add a motor and a cable. And then this will be used in calculating the surface power, right? But I'm not going to do that. So let me just uncheck. Let me just focus on the hydraulics now. So this is the pump data. This is the number of stages. Now, if I go to my nodal analysis, let me show you that I'm going to run two cases. One with the ESP installed. I'll go to operating frequency, which is 60, and one with the ESP turned off. And you will see now that I'm going to have one IPR curve and two VLP curves. Each VLP represents the ESP. So this is when the ESP has 0 frequency, and this is the VLP with the ESP of frequency of 60. Okay. Now, I can now go and due to the time, we need to cover more options. So I'm gonna now delete the pump, and now I'm going to install a gas lift. So I can also go to the gas lift design. Now this is a very sophisticated and comprehensive gas lift design capability. I will not, of course, be able to cover all the options. I will just highlight the main high-level options here. Like, for example, it is asking you about the what is the outlet pressure. So the outlet pressure will be 300. Okay. Now the operating in the injection pressure. So how much available of injection pressure we will have at the casing head. So I say, for example, I can provide up to 1800 psi, and then the casing, the surface injection temperature, say for example, maybe 100 degrees Fahrenheit, and the target injection rate. Okay, so let's say, for example, I'd like to inject around maybe 2 million. So now with these conditions, and then I can put the valve selection filter. This is based on your manufacturer or your contract with the available provider, the valve size, and then you can also generate a report. So this is available in the latest release, which is coming in 2 weeks. And now again, I will not be able to cover all these options. But then when I click on run, what will happen here is that the casing head pressure is going to be used to design an ESP, a gas lift system for me. Okay. Now, this is the gas lift design report, the comprehensive gas lift design report. That if you have taken a gas lift course or you're working in gas lift, you'll be familiar with this curve. So this is basically the injection pressure in the annulus. Okay. This is the opening pressure. This is the closure pressure. Okay. And now if you go to the summary here, if you go to the grid, then it will tell you that with this design, you are going to produce this much amount of flow rate, of liquid flow rate. And now this is going to be the unloading gas rate. And if you want to see how much you are actually injecting, you can go to the you can go to the column, select columns, and then you can select the gas rate. So as you can see here, this is the gas injection rate. This is but under these conditions, this is going to be one of the unloading valves will still be flowing. Okay. Now, suppose that I'm happy with my design. As you can see here, I mean, if you are a powerful gas lift design engineer, you will understand all these options and you can play with them. And now I can simply go to the design results and then I can install the design. Once I click on install the design, the gas lift valve will be installed automatically. I can also click on generate the report, and then it will tell, okay, where do you want to store it? Let me just say I'm gonna store it, let's say, for example, at the C drive. Once I click on save, okay, yes, it's going to open it immediately for me as a PDF format. This generating the report is not available in 23. It's available in 24, which is coming very soon. So this is the gas lift design report that you can use and give it to your field to your field operations to install these valves. And this is the gas lift report. Sorry, the design plot. And now, once I have done this, now you will see that all my gas lift valves have been installed. Okay. And now you can run the advanced gas lift calculation by enabling the multi-pointing. You can specify the injection pressure. We just start with 0 here. So now using this injection pressure, Now the valves are installed. Okay, so now you can run your PT profile under 300 wellhead pressure, and now we will be able to run the advanced gas lift calculation, and it will tell you the status of each of the valves. Like for example, I can go to the diagnostic results, and then I can go to the show grid, and now we can see now the status of each of the valves. Like for example, we're injecting this amount at the bottom valve, this amount of the middle valve, which means that we have multi-pointing, and both of them are throttling. So this is a situation that you need to avoid. So you better play with the gas injection pressure and maybe change the design if you want. Okay. So yes, so this is for the gas lift. Let me also remove these three gas lifts, and I know we're running out of time, but now let's also go to the artificial lift, and then I'm gonna install, let's say, a rod pump. Okay, so the rod pump is simply, we don't have a rod pump design or PCP design, but we can install and model the rod pump. Like for example, I can say that my rod pump here is the depth is, for example, it goes up to, let's say, 7. Of course, you know, rod pump is not suitable for such high depth, but what, you know, it's better. What I can do is that I'm gonna open one of the ready-made examples for rod pump calculation. So I believe we have, so this is a rod pump simulation. Guys, you can start typing your questions on the chat so that we can have a look. So as you can see here, this is the rod pump. So this is, we can model the rod pump by either the stroke length and the frequency. Like for example, here we have so this is a strong pump which is 12 strokes per minute. This is the stroke length, okay, and this is the depth. Now, once I install this rod pump with all its details, I can simply, if I go to the PT profile, I will run, and then I'm gonna see the impact of the pump. And I can, of course, also sensitize on, for example, the number of strokes. Let's say strokes per minute. Like for example, if I say, give me let's say 60 and 120 strokes per minute and step 60. So these are two cases. Okay, this okay, sorry. Per minute, yeah, sorry. So 5 to, let's say, 30. 5 and 30. As you can see here, these are the two cases using different stroke length, stroke per minute, and then this is the affected flow rate. Finally, I'm going to show you the PCP. So another case example for a PCP, which is progressive cavity pump. This is the PCP. Now under the PCP, we have what is called the slip factor. Okay, we have also a catalog of PCPs. This is the nominal diameter. This is the operating speed, and this is the slip factor. Okay, the slip factor will change the behavior. Like for example, this is the corrected flow rate. This is the original one, and basically the slip factor will adjust the pump performance to account for wear and account for the efficiency of the pump, or at the same time you can play with the head factor or the flow factor or the power factor. All these are parameters to fine tune your PCP calculation. There are, of course, also other calculations, such as you can have a separator as part of the gas separator as part of the PCP. And now when you run your nodal analysis, or let's at different reservoir pressure and different PCP operating speed, then you will have these sensitivity cases. So each of these outflow curves represent the speed. Like, for example, we have now two speeds, 100 RPM and 200 RPM. So that's why we have two outflow, and we have the three inflow depending on the available reservoir pressures. I wish I have more time, but I hope that I covered as much as I can when it comes to the well modeling capabilities. So we, just to recap, we talked about the black oil and compositional. We showed you how we model the compositional fluid. We showed the different IPR, like, for example, if it's a vertical geometry single point, and then you have multiple IPR methods, like, for example, if the fluid is gas, you can use the back pressure equation. We showed you also how to use a horizontal IPR, like Joshi and Bawanode, and each one has its own input. We covered also Darcy, the scene calculation. I showed you also some example on surface equipment, like, for example, in this case, we are having a choke, right, and a flow line. As part of our calculation, we can include that in the calculation. We can, yeah. One last thing I didn't cover is when we have multiple completions. There is one example here. If you go to the case studies, there is okay, where is it? If you have PipeSim installed, you really need to explore these different examples to have an idea of the different options that we have. Like, for example, here we have horizontal multi-layer well. Let me see here. Horizontal multi-layer producer, in which you can model each completion, alone. Like, for example, in this case, we have, if it's horizontal, so each of these these completions is modeled in a different IPR method. Like, for example, the last one, we are using the distributed productivity index, in which you specify the PI per length. So this is 0.12. If you multiply by the length, you get the total PI for this IPR. For this completion, we're using Baba and Ode, and this is the input for Baba and Ode. This is another a horizontal completion using Joshi IPR with different IPR methods. And now, when I run my nodal analysis, or my PT profile for that matter, I can define the contribution of each of the completions. So if you go to this is the total production, but if you go to show grid, now starting from bottom up, you can expand. If you click on expand all, you can expand the different completions. So each of the completions is contributing. Like, for example, the bottom completion here at this depth is contributing 8,000. The other one is contributing gas rate. So you can actually combine oil IPR, oil completion or gas completion. And the last one is contributing no, this is not the contribution. This is the total rate at this depth. Yeah, the contribution. What is the contribution? I believe the contribution is you'll need to see the difference here. Like, for example, in this case, this is the upper completion. So if I go to the liquid rate, we just add the liquid rate, stock tank, liquid rate, stock tank liquid flow rate. So as you can see here, when I add that, you will see that this is how much each of the completion is contributing. Like, for example, this is now contributing 2,000, and now then what is the different completions? Yeah, let me just not expand all. Yeah, so now this is the what's wrong here? I think we have a problem. But anyways, I need to look into this later on because this is the total. And then if you scroll down, so this is the difference here for this for this completion. And now this is the middle completion. So I need to, yeah, I have to look into this because this doesn't this does look correct. But anyways, one last thing before we continue. If I change this into an advanced well, then this is going to be modeled using the network solver. And now we are going to have a better, representation of the contribution. But I need to first go and cover the last point, which is 15100. And now if I go to the system performance, when I run this, now we are going to see, using the show grid, we are going to have more details about each of the completions. Like, for example, right now, this is the middle, this is the upper, okay? So this is producing 300. This is the middle, 4,000. And this is the upper. What is the upper? So this is the upper, this is the middle. And where's the bottom? Completion. Here is the bottom completion. Okay, so this is contributing 8,000. So when you combine that, you will see the total at the surface. Okay. Now, what else? Yes, I believe that's all. So now, I wish I have more time, but we already took 1.5 hours. So let's now focus on the questions. So I will go to the chat. I will start asking the questions one by one. So ESP give you higher rate than gas lift in this case, or we can adjust gas rate injection to accommodate it. Well, it all really depends on many factors. Like, for example, if I go to the gas rate and I tell them, okay, I'd like to inject more, maybe I will be able to inject to achieve more rate. And also there is one calculation in PipeSim where you can actually put a valve and then immediately, as I showed earlier, just inject as much as you see, just to see how much you have as an impact, because it could be that adding gas rate will never reach to the rate that an ESP can give you. And this is because in the ESP we told them this is how much we need to produce, and he told you, okay, you need to install all these pumps. So we are controlling how much pressure. Whereas in the gas lift, there will be the gas lift opening and closing. There will be the gain that you will get from lightening the oil, and of course the control there is not the same as the ESP. Gas lift is also, this is from Mr. Ibrahim, gas lift is also successful, but optimization is needed. I agree, that's true. How can I know the best fluid package for my model? Well, in PipeSim, we have different composition fluid packages, and each one has a list of equation of state. Like, for example, symmetry is an internal SLB product, which we have tested and verified. Multiflash is also another powerful package from KBC that has been with PipeSim for many years. So you have to decide, really. I cannot recommend one over the other. Everyone has its own strengths and advantages. The case sensitivity would be very complicated for commingled production scenario. Am I right? So if you can speak up, Mujahid, and tell me what do you mean by commingled production scenario? Is it for the multi-phase flow, this one here? So in this case, if I want to run PT profile, if I switch back to production, not the advanced well, let me just open the case again. Sorry. Multi-phase from multi-perforations. Yeah, I mean, all that is taken into consideration. So the mixing will happen based on the gas content, the water content, all that will happen, and the mixture will be calculated by the engine. Yes. Any more questions? If I have only production data history without PTA, can I figure out using PipeSim how much is a formation damage skin and mechanical skin separately? Well, not the skin, but you can enter your downhole data. Like, for example, if I show you, let me just open the basic oil well. And in this case, suppose that you have only, if you have, let's say, only rate, for example, and you'd like to calculate a PI, right? Like, for example, here you say, okay, my PI is 5, and then if I run my model in this case, okay, let me see how much am I producing. So in this case, based on this PI, it's producing 7,400, 7,500. And you say, but no, I am producing 5,200. I need to calculate the exact PI. Well, you can do that. If you go to the PT profile calculation, there is a specific calculation that tells you calculated variable is custom. So when you click on custom calculation, you specify the exact rate. Let's say the exact rate is 5,200 liquid rate. And then you'd like to calculate the completion and the PI. And then you say, okay, the PI is starting between, let's say, 0.1 and 5. Now, what will happen is that PipeSim is going to automatically, using this square method, is going to it automatically calculate for you the exact PI that will give you that rate, which is in this case 2.32. So now, without the pressure transient analysis data, I can simply take 2.32. I go to my completion, I put 2.32, and I'm done. My well now, if I solve for the rate, is going to give me 5,200 almost. See? So this is a very simple calibration that can be done quickly. You will be able to calculate the exact PI to match a certain rate. I hope that answers your question. Okay, what's the major addition in 2024? It's basically the dual strain calculation. So just I will give you a glimpse quickly on the 2024. So let me just show you quickly. This is a teaser for anybody attending the OPA session today. So if I go to this one here, and then I go look into this this scenario here. I'm telling you, you will never find any software that can do this today. We have a dual string in the same well, in which the short tubing is producing from one completion, the long tubing is producing from another completion. I'm separating them with a packer, and then I am defining how much injection is going to each of the tubings. And then when I run the system profile or system performance, I can define the wellhead pressure for each of the strings, the long and the short. Okay. And now when I click run, I will be able to see the performance of each of the strings while I'm using the wheel canvas. So each of this, so this is the production. If I can, for example, say I'd like to say the flowing completion 1 to short tubing, and then the short tubing stream outlet, and then CPL1. So as you can see here, this describes the flow for this branch here. And I can also look into the other completion. This is the other completion, which is here. And then flowing CPL to the long tubing, which is this branch. And then the long tubing outlet. So this is now describing the flow in the other branch. This is all in the same well. There are certain places in the world where they have this kind of configuration in which they have dual strings. You can have production and injection in the same well. Like, for example, you can inject in the long tubing to go to the water aquifer and produce oil in the shallow aquifer. I think this is available probably in Kuwait. We have also in Malaysia, Petronas, they have a lot of dual string gas lift systems. The same in I think in several operators in Africa. So this is the main addition in 2024. Okay, another question. Is it similar to the critical rate equation, Myers gradients method, or Chaperson method, or the operating point based on the inflow performance relationship? So are you talking about the what are you talking about when it comes to the critical rate? So are you talking about for the sand, or are you talking about the liquid loading? Can you please the Q operating point based on the inflow and the outflow relationship? Can you clarify, please, Randu? Question number 2. If we have issues with preventing coning or channeling, when we calculate using the flow rate, critical oil flow rate is not similar to the operating flow rate. Okay, which is a good reference for GDs? That's a good question. So what you can do, let me just show you here. One of the things that we enable in the nodal analysis calculation, we go to the nodal. We just run without any sensitivity. So we do have these buttons here. It says, show me the bubble point and view the operating envelope. So in this case, probably this is not a good example because now we are already intersecting in the unstable region. But look, this is the bubble point. Okay, so you would like your intersection not to happen below this bubble point pressure. This bubble point pressure is calculated using, of course, the PVT correlations that I have. Okay, or if you use composition, that's going to be using the composition phase diagram. So I hope this answers your question. So the intersection between the inflow and the outflow should happen above the bubble point line. Okay. Okay. How to calculate the VLP equation on PipeSim SLB specific to the method? How to calculate the VLP equation on PipeSim SLB specific to the method equation? I really did not understand the question, but the flow. One of the questions probably is how to select the VLP correlation. So if you go to simulation settings, you will see the vertical and the horizontal flow model. Of course, in SLB, it is recommended to use OLGA-S. In 2024, we have added OLGA-S steady state flow model 2023. And the reason this is not the default is because this is needs a license, so you need to purchase this. But you can select any of the correlations for the VLP calculation. This is available under simulation settings. I hope this answers your question. Other question, can we do the same to check the gas lift is working properly or not? Let's say detect multi-point injection. So yes, exactly. So this is what I showed you before. When you enable multi-point calculate, because look, if you have a case, let me just show you. If you have a one of the gas lift cases where you're using injection valve system, let me show you here. Like this case, for example. This is a case that is installed with PipeSim under the case studies, where we have injection valve system. Now, the basic calculation is that you do not enable multi-pointing. So you go to the PT profile, and then this method uses what is called deepest injection point. So all the fluid based on this injection pressure is going to go to the deepest injection valve possible. So this is one of the calculations that's available. Then when you go to the valves, you can see that, okay, this valve here is injection 2.85 and the rest has nothing. So this is without enabling the multi-pointing. So in this case, the injected rate is going to the gas rate is going to go to the deepest gas lift valve possible. The moment you enable multi-pointing, this is a more complex calculation. Okay, and this will run the diagnostics in addition to the PT profile, and then this will tell you whether you have multi-pointing or not, what's the status of the gas lift valve, whether they're throttling, open, close, and so on. Like for example, in this case, I can just go to the diagnostic results, and then I can show grid, and then it'll tell me. Now, in this case, as you can see here, many valves are actually open, and you are injecting. This is the multi-pointing calculated, okay, using this injection pressure. And as you can see here, in this case, we are injecting even much more than the we are injecting 7.4 almost. Okay. So I hope this answers your question. Good presentation, some insight. Thank you. Okay, this is the feedback. Please, add the fill the feedback form in the chat.